When you think about modern astronomy, what comes to mind? Probably giant telescopes, right? But one of the biggest challenges isn't just building the thing, it's pointing it. We're talking about aiming this massive, incredibly complex machine with a level of precision that's, well, it's genuinely superhuman.
To really wrap your head around this, let's try a little thought experiment. Imagine you're out there trying to hit a target.
And that target is incredibly small. Let's say it's just the size of a coin. Tough for sure, but maybe doable.
Okay, now let's crank up the difficulty. You have to hit that same coin, but from 2 miles away. Suddenly, this has become a monumental challenge.
But here's the real kicker, the final mind-bending twist. You're standing on a spinning platform, which is, planet Earth, and that coin is also drifting across your view. That, right there, is the everyday reality for an astronomer.
So how in the world do they pull this off? How do they hit that cosmic bullseye night after night? Well, the answer is this fascinating blend of precision hardware and incredibly sophisticated software. And we're going to break it all down by looking at some amazing research from the University of Geneva on their Euler Telescope.
All right, so the very first piece of this puzzle is just knowing where to aim in the first place. I mean, it's a big sky, right? It's just like sailing the old oceans. You can't find your destination without a really reliable map and a coordinate system to navigate the vastness.
So, astronomers basically have two kinds of maps for the sky. The first one is the horizontal system, and it's totally what you'd expect. It's just how high up is the star and which direction is it in. Super simple. The problem is, because the Earth is spinning, those coordinates are changing every single second for every star. That's why the pros use the equatorial system. Just think of it like latitude and longitude, but painted onto the sky. A star's address in this system is fixed, which makes it the absolute gold standard for catalogs and any kind of precision work.
And you can see how these two different maps lead to two different kinds of machines. On the left, you've got the altitude azimuth mount. It's simple, it moves up, down, and left-right, just like a camera on a tripod. But check out the equatorial mount on the right. See how it's cleverly tilted? That's the genius part. It's built to perfectly counteract the Earth's rotation with just one smooth, continuous motion to keep a star in its sights.
Now, the telescope we're talking about today, the Euler Telescope, uses that alt-az mount. For these huge, modern telescopes, this design is actually way simpler to build, more stable, and more cost-effective. But there's a trade-off. That simple hardware creates a really complex software problem. The telescope's computer has to constantly be calculating two different movements just to follow the smooth, curved path a star makes across the sky.
So you've got your cosmic map, you've got your hardware. You just punch in the coordinates and the telescope goes there, right? Yeah, not so fast. This is where the machine itself starts to get in the way.
The hard truth is, no machine is perfect. Every single telescope, no matter how beautifully it's engineered, has tiny, built-in flaws. We're talking about microscopic misalignments and physical imperfections that all add up, causing the telescope to point just slightly away from where you told it to go.
So where do these pesky errors even come from? Well, they get sorted into two main buckets. First up, you've got the geometric terms. Think of this like the telescope's skeleton just wasn't put together perfectly straight. Maybe the main axes aren't at a perfect 90-degree angle, or the whole structure tilts by a tiny, tiny fraction of a degree. But then you've got the non-geometric terms, and this is where things get really tricky. We're talking about the telescope's tube literally bending under its own weight as it moves. The metal expands and contracts when the temperature changes. And get this, even our own atmosphere bends the starlight before it even gets to the mirror. It's a whole mess of tiny interacting problems.
So if you can't physically build a perfect telescope, what do? Well, the solution is just beautiful in its elegance. You don't try to fix the hardware. You create a digital correction map for the software.
Here's how they do it. It's a process called building a pointing model. First, they systematically point the telescope at a whole grid of stars all across the sky. Stars whose positions are known perfectly. At each point, they measure the error, the tiny gap between where the telescope thinks it's pointing and where it's actually pointing. Then all those errors get fed into some powerful software that creates a mathematical model, basically a digital map of all the telescope's unique little flaws. Finally, you load that map back into the telescope's brain so it can apply these corrections on the fly in real time.
Okay, so that first step is absolutely crucial. To build an accurate map, you need really good data points spread evenly across the entire sky. But what's the best, most efficient way to lay out that grid?
On the left, you can see the traditional method, a simple spiral pattern. I mean, it works, but you can see how the points kind of bunch up along those arms, leaving big empty gaps in between. But look at the right. The researchers tried something different, a biased Fibonacci grid. Notice how much more evenly spaced those points are? There are no big gaps, which means they're getting a much more uniform and efficient sample of the whole sky.
Now this is the part I think is so cool. Where does this pattern come from? It's not just some random mathematical trick, it's literally nature's go-to solution for efficiency. This is the exact same mathematical pattern that tells a sunflower how to arrange its seeds, or a pine cone how to arrange its scales, all to maximize packing in exposure. It's high-tech astronomy borrowing an idea directly from biology. How cool is that?
And boom, here it is, the final product. This is that digital correction map we've been talking about. The colors are basically showing how big of a correction the telescope needs to make and in what direction, depending on where it's looking. And you can see these really clear patterns, right? The biggest corrections are needed down near the horizon, which makes sense. That's likely caused by things like atmospheric distortion and the telescope's own weight making the structure bend and sag as it looks down.
So, the map looks impressive, but did this elegant digital solution actually work? Oh boy, did it ever. The results from the Euler Telescope were, honestly, just staggering.
Before applying any of these corrections, the telescope's raw pointing error was about 300 arcseconds. Now, an arcsecond is an insanely small unit of angle. There are 3,600 of them in a single degree. So what does an error of 300 of them even mean in the real world?
Well, let's go back to our analogy. An error of 300 arcseconds is like aiming for that coin from 2 miles away and missing by more than a foot. You're not even close. You're not even on the board.
But after they created this new pointing model and plugged it into the control system, the error just plummeted. It's now less than 5 arcseconds. That is an incredible 60-fold improvement in accuracy. 60 times better. In our analogy, that's the difference between missing by a foot and landing dead center on the coin. It turns a complete miss into a perfect bullseye. Okay, so hitting a cosmic bullseye is a fantastic technical achievement, for sure. But so what? What does it actually mean for the science? Why does this level of precision matter so much?
The payoff here is just immense, and it all boils down to one word: efficiency. Every single second you're not wasting trying to find your target is a second you can spend doing actual science. This precision is what lets astronomers do the most cutting-edge work, like detecting that tiny dip in light when a distant exoplanet passes in front of its star. Ultimately, it means more data, more discoveries, and a much faster pace of unlocking the universe's secrets, all from a single night's work.
So in the end, you have this incredibly sophisticated digital map that's correcting for the invisible physical flaws of a giant machine, all so we can get a clearer picture of the universe. And it kind of makes you wonder, right? What other invisible digital corrections are quietly humming away in the background, making our modern world possible?